My name is Tyler Canham, and this is digital sampling and vibration noise analysis of rotating objects. This is the data that was collected prior to week 2, which then was gone over in lab. So if you need to take a look at it, it is here. Using the different things that we learned for digital sampling of time history and power spectrums to study waveforms from the previous weeks, I wanted to see if it was possible to tell the rotational speed of an object by using frequency analysis, and more specifically on my longboard. For the experimental procedure, I used the LabJack T4, an audio breakout adapter, 3 male jump wires, the MIDAC software, a microphone, as well as my longboard. For the experiment itself, I played different frequencies of 50, 200, 1,000, 5,000, and 10,000 through the audio jack and measured, as well as playing it from a speaker into the microphone and measuring that as well. I then went on to use the skateboard and measure the sound emitting from the speeds of 5 kilometers per hour to 35 kilometers per hour in 5 kilometer per hour increments and held and recorded at each speed. The relative response, which can be seen here in the different tables, is comparing the microphone and audio jack by dividing the microphone power spectrum VRMS by the audio jack. And you can see and then scale this to the current data that you actually get through the microphone to make sure that is accurate. My hypothesis is that the peak frequency that would be measured at the lower frequencies would relate to the speed of the actual skateboard itself, and that was displayed on the controller. So you can see that on the calculation on the following slide. Calculation, which is the conversion from speed in kilometers per hour to hertz, shows you the different calculated frequencies for each of the different speeds that the skateboard would be getting measured at to basically set a benchmark of what to look for. However, unfortunately, when this data was actually plotted, you can see that there is no peak frequencies that are being shown as where they thought they should be. This is a combination of there being a lot of noise that occurs at 0 hertz, both in the test run and the actual run, as well as it possibly also being that there is not enough sampling at the lower frequencies to really tell if there are any distinction in peaks. Therefore, a different approach was taken. So instead of looking at the different frequencies, we decided to look at amplitudes of the different groups of frequencies themselves. These frequencies being 800 hertz, 2300 hertz, and 5000 hertz were looked at, and most likely are due to some sort of electronics on board, such as PWMs or pulse width modulation. It is also possible that a commutation frequency could be being seen, especially at the lower frequencies, which end up being a multiplier of the original mechanical frequency with the amount of pole pairs present. Basically, those are the magnetic pairs that are present that are having electricity sent to them on the motor of the skateboard. So going through each of the different speeds one by one, you measured the 800 hertz, the 2300 hertz, and the 5000 hertz, as well as the average amplitude, and also the commutation frequency if it was available, and the different possible pole combinations as well. This is the analysis for 10 kilometers per hour. This is the analysis for 15 kilometers per hour. This is the analysis for 20 kilometers per hour. This is the analysis for 25 kilometers per hour. Analysis for 30 kilometers per hour, as well as the analysis for 35 kilometers per hour. We can see that the amplitude increased with speed each time, as seen by the data results below. And also it seems to be that the common pair groupings are 8 pole pairs as well as 12 pole pairs. So taking the data that we just collected and graphing that as VMS versus the kilometers per hour, we wanted to see the biggest correlation between the two, and you can see using the linear curve fitting on the side that the 2300 hertz and the average amplitude are the closest to a linear relationship. And so those will be used, and because they're the most likely consistent and also linear. So using these equations with MATLAB, you're able to equip a linear regression line to come up with the following equations below, which can be seen listed. And that can be used to predict what speed you're going at based off of what your input VRMS is that is being measured, the grouping of either 2000 to 2500 hertz, the max VRMS there, and then also the average of the entire power spectrum itself, and then being implemented into the average amplitude equation. However, when it came to pole pairs and commutation frequencies, it was not as lucky. There was not able to be seen a true commutation frequency as there is a large noise grouping at 800 hertz and also a large noise grouping at 0 hertz that seemed to drown out any peak frequencies in between, as well as the fact that due to the sampling rate, there might not have been an ability to have any substantial peaks as well. During the experiment, there's many different mitigations, such as having a silent room, a fixed mic, and also doing multiple runs, and also doing scaling from the relative response. But there were still complications, such as low frequency noise of 0 to 25 hertz being present, as well as the sampling rate maybe not being high enough for the experiment. While the experiment was not an initial success by utilizing low frequency peaks to accurately predict the speed, it was able to actually accurately predict the speed by utilizing the amplitude of the power spectrum instead.